Falling Walls Circle, Challenges and Foresight. Welcome to the Falling Walls Plenary Table. Perspectives and Challenges in Quantum Computing.
Welcome, everybody. Welcome to the table on perspectives and challenges in quantum computing, supported by 6 quantum ecosystems in Germany. My name is Martin Wiarda. I will be your moderator. I'm a journalist of education and research. The expectations are high. Quantum computing could prove to become a revolutionary technology in many fields. We are talking new ways of discovering drugs, redefining cryptography, and speeding up the development of artificial intelligence. So there is a lot of hope and also hype out there. But this planetary table is not about a hype, but about serious and honest assessment of the here and now. In addition, we're going to talk about the future, about obstacles, and yes, about opportunities. And all of this with a very distinguished panel of international experts, which now I would like to invite onto the stage. Please welcome with a warm applause Juan, Ignacio, Cirac, Sabrina, Maniscalco, Andreas, Wallraff, and Horst, Weiss. So let's start with a short round of interaction. Sabrina, you are a professor of quantum information, computing and logic at the University of Helsinki. You also are the CEO and co-founder of Algorithmic Limited, a startup focusing on quantum algorithms for life sciences. Juan Ignacio Cirac, you are the director at the Max-Planck-Institute for Quantum Optics and honorary professor at the Technical University of Munich. Also, a warm welcome to Andreas Wallraff. You're a professor for solid-state physics in the Department of Physics at the ETH in Zürich. And Horst Weiss, you're vice president Next Generation Computing at BASF in the Global Digital Services Division. And you were appointed to the Expert Council for the creation of a national roadmap for quantum computing in 2020. We have about 45 minutes of time. We'll start with a moderated panel, and later on you will be invited for a Q&A session in the audience. So let's start very basic. I'm not an expert in quantum physics. Most of the people here in the room probably are not quantum physicists. So Ignacio, when we talk about quantum computers, what types of problems they are able to solve, and what are their actually advantages? So maybe you can give us a very short impression of what is so special about quantum computers, quantum computing.
Well, quantum computing is a new way of doing calculations. It's not faster, it's different. It's based on different laws of physics, which are quantum physics. And we know that this gives us advantage in some problems. So there are some problems that with a classical computer, with a standard computer, could never be solved, whereas with a quantum computer, if we had it, it would be solved, would be possible to solve. These problems are connected to solving problems that are interesting in science, what we call quantum simulation, problem in the fields of physics, the fields of chemistry. Problems related to cryptography, actually decrypting cryptographic systems, and a few other problems. Mm-hmm. But I would say that what is important is that most of the problems are still to be discovered. We don't know. Mm-hmm.
So, Horst, why are those quantum computers better at solving those specific problems? What makes them better in solving cryptography, for example?
The quantum computers follow a different paradigm, not the von Neumann. They are, as Ignacio said, totally different. They are working instead of these two-state qubits, two-state bits are working qubits. And these qubits are represented by quantum mechanical particles, or states in general, and they can, in superposition and entanglement, then act as one effective particle. If you can exploit with a suitable algorithm this parallelism in the representation in the qubit state, then you can have a huge speed up for certain properties. And cryptography, in 1994, I think, Martin Shaw published his seminal work on the factorization of large numbers. And that is the basis for, of course, this public key stuff. So if you can decompose those big integer numbers in an efficient way, and quantum computers promise to do this in a polynomial way, then you have a huge advantage. So this is, I guess, why at least in the world the research started so intensively. Mm-hmm. Afterwards, of course, there have also been publications which interests us, for example, in the materials and molecular space that are capable of solving electronic structure problems in an exact way. And that's why we follow it in the industry.
So you said promise, you said if, then. So Sabrina, where are we yet? Are we talking about promises? Are we talking about concepts? Are we talking about ideas? So the current state of quantum computing, how would you describe it?
Well, I would say that certainly there has been a remarkable progress, and this is verified at several levels, not only at university level, but in the startup worlds and also when it comes to industry. So I think that the ecosystem is growing, and I think that nowadays already the fact that we are able to perform controlled simulations and controlled computations with hundreds of quantum bits. Of course, they are not perfect, and of course, there is a lot that needs still to be done, but I personally believe that we are really reaching a moment in which we will start to see the first useful applications of quantum computing.
But at the same time, you said, now there are not yet useful applications.
I don't think that, well, we should distinguish between useful for scientific research or also commercially useful. Of course, even when it comes to scientific research, there have been several demonstrations for certain modalities, for example, analog quantum simulators, of clear problems that quantum computers are naturally good at, but we cannot claim that there is any advantage from the industrial point of view. So we would, my perspective is that soon we will see type of quantum computers that will be able to contribute to research in ways that are complementary to what classical high-performance computers can do. So just to go back to what was mentioned before, we do know that quantum computers will not replace classical computers. They will complement them. They will be able to, working together with classical computers, allow us to do computations and simulations that are not possible otherwise.
Andreas, do you agree? Will I never have my own quantum computer at home like I have my home computer now, my personal computer? This is not the future?
Yeah, at the moment it seems unlikely that you will have your own personal quantum computer, at least on a large scale at home. Maybe at some stage you might have a toy one or so that is fun for playing around with. So quantum computers do exist these days. So we have quantum computers with several tens or maybe in instances several hundreds of qubits. And many different problems have been solved on the toy model level. So there have been applications in quantum chemistry, for example. There have been some optimization problems that have been solved. But these are all very basic instances of these problems. And what we would look for in the future is really a large-scale quantum computer that can solve arbitrarily complex problems in these areas. And this might still take some time because this will likely require hundreds of thousands of qubits rather than a few hundred ones.
Define it will take some time?
Yeah, so I think we're in this development for the long run. It will certainly take 5 to 10 years to reach these goals, and it might also take a little longer than that. So I think long, continuous, sustained development is required to really reach the goals that we're having.
So Sabrina, you have your startup company, so obviously you believe that there is also some economic value in the near future for you? So
yes,
would you agree 5 to 10 years? So what is your personal perspective on that you decided to found the startup?
Yes, yes. Of course, one aspect to consider is that nowadays research and development is not carried on only by universities, but it is also carried on in the companies and in startups. And therefore, for certain perspective, we do not know fully and completely what is the level of readiness of this technology, because many companies are not disclosing their knowledge. Of course, it's clear, so personally, I believe that it will not be necessary to wait until the moment in which we will have millions of qubits in the so-called fault-tolerant or error-corrected paradigm. But I know that other scientists disagree. So this is, again, within the scientific community, there is debate about when this will happen. Clearly, the moment in which we will have a fully error-corrected, fault-tolerant quantum computers, we will be able to tackle problems of a complexity that will be remarkable with respect to before. But I also think that the paradigms that we have today, so smaller and still noisy, will allow to have useful and also commercially relevant in the next 3 to 5 years.
So let's make it more concrete. And Horst, why is the BASF in there? What's your interest? What concrete expectations do you have? Where do you see applications that can pay off for your company? Be as concrete as possible.
Yeah, so I already mentioned one. One is, of course, the whole field of, you mentioned drug discovery, I would say catalysis research, stuff like this. Everything that tackles this electronic structure problem where you try to compute with quantum chemical methods the behavior of materials and so on. You want to have exact solutions if possible. And at present, I can tell you when we use our supercomputer, we have one at BASF for this support of modeling, but if we try it for tiny problems, even tiny problems like metal ions in a solvent, and we want to see the complexation power of selectivity of certain agents to this. If we try to do it exact, not with heuristics, but exact, we will fail, even with systems that contain only 20 atoms. And this is because of the scaling behavior of these exact quantum mechanical methods, if not running on a quantum computer. If, and this is mathematically proven, we are able to put it onto a fault-tolerant quantum computer, of course, in the future, then we are good to go. Yeah, then we will have a massive speed up there. In the field of optimization, I mean, every company needs to optimize everything, right? Logistics, the supply chain, in our case also the chemical apparatus and all that, right? These optimization problems are also a candidate, but there the matter is way more complicated. And it is so complicated because for this type of NP-hard problems, nothing is proven yet, so we don't know. But there are so many super smart people in the world examining exactly these fundamentals of this and try to find also new formulations for this topic. And that is, of course, something that we won't want to miss. The last topic is in the field of quantum machine learning. Machine learning nowadays rolls over all of our activities in the space of simulation and whatever we do in the company, right? It's an extremely powerful tool. And what we also start to heuristically investigate is if the data expressivity given this type of quantum algorithms is better. So in other words, that we can train models more accurate with less data. This is also something that is in the open space. This is our view. So there's a complexity for which we hope we can find faster, better solutions using quantum computers. On the other hand, we see that the big tech companies like Microsoft, they also go now from their perspective as huge digital champions in our domain. So Microsoft, for example, has hired people for investigating catalysis. At the moment, we start to discuss also how to collaborate on certain levels. And I think if you are blind in the field of this super emerging technology, which we need to master, because in my opinion, it's one of the fundamental technologies of this century, you will fail. So we need early gather the experience and the know-how. And this is why we are in. We cannot afford not doing it, I would say.
Ignacio, what's your favorite example? What motivates you to do your research as a Max-Planck director on quantum computing? So what's your favorite possible application in the future?
Okay, so, well, the first thing is, I want to say that we are in a very special moment in the sense that there is a device that is working and it's able to solve a problem that we cannot solve with classical computers. This problem is academic, so it doesn't have any industrial or scientific application, but this is a fact. So what we want to do now is to try to see if there is, with the same device, even if it's not perfect, it's not big, whether we can solve some other problems that would have either scientific interest or industrial interest. Now, what I think is that industrial interest, and it was mentioned before, that's not so clear. So at the moment there are many uncertainties, and we don't know if these small devices, these, let's say, not perfect devices, will do that, or how long it will take until they do that. However, for scientific research, we already know, and we have a very good basis to know that there are applications. So there are problems in science, I'm a scientist, so problems in physics, problems in chemistry, problems in some other areas that I cannot solve with supercomputers, and I would be able to solve with these small devices. For example, what is called the problem of superconductivity at high temperature. So there are some models that exist that tell you that when you have certain experiments, something is occurring, and we don't know if these models really describe what is happening in the experiment. And the problem there is that in order to check that these models really represent what is happening in the experiment, you have to solve these models. And for that, you need computers, and with standard computers or supercomputers, you cannot solve them, and therefore, you cannot see if this is really the model for this mysterious effect. However, with quantum computers, then you could solve, in the way that you said before, you could solve these models and answer the question whether this model really represents what is happening in the experiments, and we hope that then this will have indirect applications because we will understand better how superconductivity works at higher temperatures and hopefully then increase the temperature at which this is happening.
Again, I hear a lot of hope, I hear a lot of promise, I hear a lot of could, maybe, if so. Let's take a step back. This kind of reminds me of nuclear fusion, that there is always big potential, but it's never now. It's always somewhere in the future. Andreas, is it a fair comparison?
I don't think that it is a fair comparison. I think one aspect that matters is how much progress there is in a field. Yeah? And in the field of quantum information science and in the development of quantum computers, there is a large amount of progress currently. So the field
you don't
really,
see that in nuclear fusion?
Maybe a little less so, yeah, but maybe colleagues would disagree there that work in this field. But there are fields that saturate when time goes on and while you try to still solve the same problem. And I think in quantum information science, there's really lots of progress. And quantum information science and the development of quantum computers is particularly interesting because it has sort of an interesting marriage between trying to answer very interesting basic science questions while at the same time having these very interesting applications like building a universal quantum computer on a large scale that could be valuable for solving big problems that we're having.
Okay, so you say that you can't really compare those two, but does it concern any of you that there is some kind of hype going on there? That there is some hype in the public? The expectations, as I said, are high, so they are towards nuclear fusion. So at some point, you will have to meet those expectations. Ignacio, does that worry you?
I'm very concerned already for several years, and I think that I know because I've been concerned about that for many years. But let me tell you something maybe related to the previous question that I think is important. You compare it with nuclear fusion, and I would compare it more with classical computation. Go back 80 years ago. So I told you that now quantum computers, we know that they are good for solving scientific problems and for decrypting messages. Do you know what were the only applications that classical computers, the first one that were built, were useful for? Scientific research and decrypting messages. So the expectation is that in the same way that classical computers have developed with time and have found many applications that we were not thinking about, this is what will happen. However, coming back to your question, now the worry or the concern is that now we will see, oh yes, for sure, this will work for sure, and this will work for the climate research, for cancer research, and whatever. And these are the hypes that are occurring, and that probably will not come to be true. The applications will be completely different, and these don't manage these expectations. It may happen that after 3 years or 4 years, people will say, well, quantum computers are useless because they didn't fulfill the promises.
Sabrina.
Yes, I wanted to also go back to the comparison with classical computers to also say that in the past, the development of classical computers was such that we only had to do better than before, while now quantum computers are benchmarked against classical computers that are a technology that has a very long past. So now what we are asking to a very new technology is to outperform a technology with a long history, and this is very demanding. Of course, it takes time, but clearly we are progressing in that direction. And about the hype, there is also to remember that I don't think specifically that the hype in quantum is very different or even more worrying than what there is in other fields. So I think definitely we have to have integrity, and we have to be honest in saying what this technology can do, but at the same time we have to find the right balance with also the fact that this is a potentially groundbreaking technology, so we need to be visionary at the same time. Where do we find the right balance? I think it's important, and it's something that many are trying to do. Often there is another variable that is the fact that we need to oversimplify and when we discuss quantum technologies, because we don't want to use jargon, and very often we need to use metaphors, so this makes it even more challenging. Mm-hmm. But the balance between really being visionary and thinking what really this technology could do, and the fact of being honest with what we have nowadays is crucial.
Mm-hmm. Horst.
Yeah, I think what you say, this element of expectation management is extremely important in this field. And I think due to the quick success that were in the publications promised in the 2015 region with IBM and Google, solving the H2 problem, for example, on quantum computers and so on. There were lots of projections that even with this NISQ type of hardware that they had at that time, there would be something, provided we have 50 qubits, something that would be doable, right? Every chemist, for example, would say, 50 qubits, 50 electrons, that's something interesting for us. If he could put it on a quantum computer and do the exact calculation, then it's cool. And now it turns out this is, of course, is not working. This is not the only problem, but you need also to process many gates in order to do the full computation. And this turns out to be more and more problematic. Yeah? The technology simply isn't there. So, and now there's, of course, some disappointment in some areas that with NISQ we can't do what we promised to do. Yeah? We will need this more elaborated computers. I would say this is unavoidable if you have this type of groundbreaking technologies that really require many innovation steps. The problem there is that you need to take care of the communication. And I think in the very beginning there were many interviews also given that would project that even with the devices there and with an incremental development and with the roadmap here and there, everything would work out. When you look onto the projections of the big companies, they all have their roadmaps. Yeah? Google, for example, they had a roadmap for milestone 6, I think it was 2029, where they were expecting to have some number of fault-tolerant machines. And they now removed this statement. So it's still milestone 6, that's their goal, to build this, but they don't know when it exactly will happen. And I think it's only fair. But the important thing to me as an industrial person is that when I look around, that all the technology leaders in the world, the big ones, the big companies, also in China, they develop this type of technology because it is so important.
Mm-hmm. Andreas, you wanted to add to that?
Yeah, I think it's very important to see that building quantum computers is a very demanding task. So it's certainly not easy. It's not only in the field of engineering now that you would need to excel to build large-scale quantum computers, but there's still room for good science breakthroughs in this advance. And maybe one aspect that one needs to acknowledge is when one reads articles in the media about the recent successes, frequently it's referred to certain application areas like quantum chemistry or optimization problems. And then frequently, it's really small problems that's been solved in these instances and not large-scale problems. And that somehow gets, at times, brushed under the carpet in these articles that you read. So maybe one thing that is a good advice is to sort of always take it with a grain of salt and look at who is communicating, or if it's a startup or a big IT company that is communicating, they of course have some interest in presenting at what stage their technology is. And certainly we all see that there's lots of potential in it, but we're not there yet. Like really quite a bit of development has to happen.
All of you are working in Europe in different positions. So let's talk about the position or the situation in Europe compared to other parts of the world when it comes to quantum computing. Maybe you can start with the corporate view there. How's Europe, Germany especially, but Europe stands, how does it stand compared to the US or to Asian countries?
So first of all, you should consider the funding situation. When we look onto China, one of the important players, you have national steering. You have a national plan. You have $15 billion for the next 6 years for investments in quantum technologies. You have big centers built in Hefei that consider all the 3 pillars of quantum technologies over there. And you have now also an emerging scene of startups also there. When you look to North America, you have the big champions who do these big programs and invest a lot of money, and are also in some areas really technology leaders. You have a moderate part with 3 billion fundings of the public funding schemes, but you have a huge scenery that does this venture capital funding. To give an example, there's a company, PsiQuantum, they got $670 million from their last series. And this is a bit more than we in Germany have from the DLR for the development or the investigation of all the 4 or 5 pillars for the quantum ecosystems here, right? This is totally a different scenario that they have here.
So Sabrina, do you agree it's not such an optimistic outview from the European point of view?
Well, of course, I agree that there are differences, clearly, and in particular when it comes to the, for example, startup world, there are significant differences between the US and Europe, although clearly Europe is catching up, but of course it's, the startup world was born in the US, and situations or cases of investment of these quantities are much more typical in the US than in Europe. But of course, for me, what is important to remember is that eventually, in order really to progress the field, we need the whole ecosystem. So we need universities, we need startups, we need big corporations, and we also need international collaboration. And this is not always easy, but we should remember that it's mandatory, it's necessary. Quantum information science and technology has always been a very collaborative field. And I think that one of the successes of this field has been because of international collaboration, and it is something that is still very much needed.
And is that something where Germany or Europe is also kind of successful when we're talking about ecosystems that are developing? Ignacio?
Yes, well, I think that Europe is very well aware of the importance of quantum computation and quantum technologies in general, especially the policymakers. I think that if you compare the funding that we have in Europe, the public funding, as compared to the American funding, is not that different. What is different is the private funding, so the private companies, the startup and venture capital, and so on.
Which is a problem in many scientific disciplines, not only
in quantum computing. And in China, there's much more public funding than in Europe, but we are not that bad, I would say. And what's good is that our politicians believe in the importance of the field, and they are aware of the fact that it will take a long time. You were saying that we're always talking about if, when. Well, so, I mean, one has to have this into account, that you're funding for something that will not have revenues next year or in 2 years. And this, I think, that is important also to take into account, because it may happen that now this venture capital or the industry, at some point, they realize that they don't have benefits with that. And in 2 years or 3 years, then they stop funding. And it's very good to have the backbone or the backup from the public funding that we have in Europe and in some other places that will still stay there.
But is it really that stable? My impression is that we have also political fashions and that maybe quantum computing, quantum science, quantum research in general was more of a fashion 2, 3, 4 years ago than it is now. It almost seems as politics already are moving on, Andreas.
I really perceive it very differently. If you, for example, look at the interests that students have at universities, I think there's just lots of students. It's much more attractive to now look into quantum information science than in other areas. Maybe 20 years ago, like a fashionable thing to look at as a student was to study particle physics and be engaged in sort of fundamental research at CERN, for example. But now there's a large amount of interest to contribute to quantum information science and its applications. And if you look at the students who sort of vote with their feet on how interesting they find the area, I would find the area is really very exciting. And I would think that there was hardly a better time to do research in this area or to found a company or be a student to look for a job. Yeah, there's just lots of opportunities, and I don't think that ever before the opportunities have been more plenty than now. So I do think things are looking really good.
So you're not afraid of something you could call a quantum winter that might come at some point, that if all the promises have been exhausted and if everything takes longer than maybe expected, that there might come up a situation where also the political funding might change, Sabrina?
Well, I think that to connect with what was said before, the role of government in de-risking for technologies that require long-term is really critical. And this is something recognized not just in Europe, also in the States. There are many examples. It has been done before. And this is what I think in Europe our politicians are understanding at the moment. And another important thing is that you mentioned before about venture capitalists probably becoming disillusioned by the fact that there is no short-term revenue. There are examples of other, for example, in the life sciences, if you think in terms of drug discovery, very often you invest for something that requires clinical trials can be very long. So there are investors that clearly are interested in investing in long-term solutions. So it is not so uncommon. Of course, the most important thing is to continue to demonstrate progress as we are doing and to engage governments to support the ecosystem.
Horst?
Yeah, I'm a bit it's difficult for me to not also see what you mentioned.
You have mixed feelings about it.
I have really mixed feelings about the situation. I mean, from the public interest, I would say at the moment everything goes towards generative AI. This is of main interest also in the companies and so on, right? On the other hand, I mean, this topic about quantum computing and quantum technologies is a long-term one, and I think people understood this, at least the people who are in command and making the plans. And I simply expect from the politics that they act accordingly, that they understand that this is important. I mean, when you look how the US government is doing it, they have a center of quantum technology coordinated directly sitting in the White House and consulting to the US president. It's a matter of fact. They also have a group of people who come from the big research institutions, including, and also the governmental institutions, including NSF and NSA and what else. And so there is a lot of national interest, and there's a big claim under a letter that was written by Biden, signed by Biden last year, where they say we simply take the following measures to ensure that the US, North America, will be the leading tech company in quantum computing. And this year we saw the next chapter, the presidential, the executive order, mitigating the business with Chinese and other countries towards the whole field of quantum technologies. All this together states that from a very political perspective, the topic is addressed and understood as of being extremely important. And of course, we cannot just follow what is written now here and there every day in the newspaper, which now says, well, AI is a new big revolution and so on, and forget about the long-term commitment that we need to give to the development of this technology. And it must be a long-term commitment, because we want to raise, for example, the generation workforce for this type of technologies, and so on. Yeah, I mean,
so we need a long-term commitment. At the same time, we need excitement about it now. Andreas.
Yeah, I do think that I would think most governments have realistic expectations. I would also think that the US government really very carefully analyzes the current situation. I think they also have realistic expectations of where this would go when you see how they define what next large-scale goals could be. So those are achievable, and those don't promise to have a universal fault-tolerant quantum computer in 2 or 3 years. They know that this will take some time. And I also do think that the governmental interest in sort of major areas of the world, in the US, in China, in Europe, this will not go away, even if maybe sort of some of the hype and has created more growth than you would otherwise have seen. You would likely now have some adjustments, maybe some startups won't be doing so well, or some big companies won't be investing quite as much, but I do think that all the good labs and the good startups and the good companies, they will continue to work on that, and I think it will be supported by governments.
All right. So now it's time for some questions from you here in the audience and also from the digital audience, and I'll look over to Adam Levy, so
Thank you.
ahead.
So to get us started, I think we often talk about quantum computers as if there's one quantum computer, but there are actually lots of competing technologies, competing ideas for the quantum computer. Is this an advantage to be trying out all these alternatives, or are we spreading ourselves quite thin by doing this?
Who wants to answer?
I could take it, yeah. So I do think that indeed there's no particular technology has been selected yet. There are a few good candidates, like ones based on ions, for example, or superconducting circuits. But the path to the finish line is still so distant that you couldn't guarantee now that you could pick the technology that would win in the end. So I think at the moment it's still wise to push on various technologies at the same time.
We've got quite a few questions from the online audience. I'll let the physical audience know. Please raise your hand nice and high so we can see you if you have any questions. Now, a question from the online chat. What about the climate crisis? When we talk about quantum computers, how energy hungry and ultimately fossil fuel hungry would computers like these be?
That's an interesting question. Also, if you compare to traditional computing, what about the energy consumption, Ignacio?
Well, that's one of the interesting speculations that people have, that so far people have been interested in having computers to solve problems faster. But actually, if they will consume less energy, they will also be interesting, and it's under investigation. Because, I mean, it's a difficult question, because you have to take into account what do you mean by the energy consumption. Maybe it's not the energy that you have the last moment, but I mean, to cool down everything or to make the vacuum, you have to take into account everything. But it may well be that because it's completely different, something that people didn't have not thought so deeply about that there might be good advantages in that. Yeah.
Who wants to add to that? That's something that you think about at BASF? Energy consumption of quantum computing?
Yeah, I mean, we've also read about speculation that they are way more efficient because they have fully reversible operations and all that. I think it's way too early to speculate about this. Yeah. First of all, at the moment, they are research machines, and you never ask for a research machine, I would say, how energy efficient is compared to what? Yeah, I mean, it's really a research machine. And
so it would be a mistake to promise too much now about it. To say, well, this is the big climate solution. It would be a problem to promise that.
I think you can't. I think it's really not from the computation. You can certainly not say that. I think an idea that people sometimes voice in this context is that maybe quantum computers could be used to make better catalysts, for example, or they could help in making even better batteries than we have already now. And along those lines, quantum computers could support this challenge with climate change, but probably not only from the perspective of reducing power consumption. And indeed, I think it's too early. It's not a question that scientists or even developers can address now to think about how they would reduce the energy consumption in the quantum computer, because we're still facing the challenge of building better ones.
I see we have a question from our physical audience at the back here, I believe. So maybe you could stand up and we can get a microphone over to you.
Thank you. As you said, there are a variety of possible hardware implementations with ions and ion traps and all the other range of solution spaces. But do you think that it may be possible to use algorithms to create topologically protected qubits so that potentially the decoherence problem can be sidestepped with using software to do error correction to create effectively resilient qubits in memory, and that we might be able to get past avoid having to solve the hardware problem?
Thank you. Sabrina?
Yes, so of course this was an important point. One of the major limitations nowadays of existing devices is really errors that are induced by noise. These are imperfect devices, and software can be helpful. So it's not just an engineering problem in creating always the most perfect and noise-protected chip, but it's also a software problem in both for noise mitigation and for error correction. And there is active research in this direction. And I would say that there is clearly progress. And I would distinguish between the noise mitigation methods that are those that in a way allow to remove errors from the existing devices without correcting them fully, so without going in this paradigm of fault tolerance, and they are already very effective. If you think in terms of, for example, our noise-canceling headsets, it's a way of through software, removing some of the errors, and this can be implemented even in the quantum context, and is already implemented. There are many proposals, of course. And then there is, again, the error correction paradigm, which is, again, both an engineering hardware and a software problem. And lots of development has been done, but I think that this will require a longer time scale to be developed. So fault tolerance quantum computer is not something that we will likely see in the next 5 years, but is really the holy grail of the field in a way. But
so we'll leave it there, take the next question. Yeah.
So we have another question from our in-person audience, and while we're getting a microphone over there, I'll just ask a quick question from online. At Falling Walls, we're all about collaboration. What about collaboration between quantum computers and conventional computers? Are we heading towards some kind of hybrid computer in the future?
That's interesting. Are they only like competitors? You know, they can do two different things, or can they do also together more than they can do alone?
Yes,
Ignacio.
indeed. So that's a very active field, and then there are already examples where we know that this hybrid can be exploited. And another thing that is important in this context is that quantum computation is inspiring algorithms in classical computation, and so there are already, even companies using some quantum-inspired classical algorithms. So, like the goal of having a quantum computer is very far away. Maybe it's an interesting one, it will take, but the path that we're taking, we're learning a lot, and we're seeing that there are some things that are already worth without having to build a quantum computer yet.
Andreas and then Sabrina.
So I think one of the aspects that is important there is not only the cooperation between the classical and the quantum computer, but it's also cooperating on this big challenge. And I think we could go much further if we were really cooperating as effective as possible. And certainly now, because of the high expectations, it's already that the companies and also nations think, and even regions within nations think that they can sort of push the development of their own private quantum computer in some sense, yeah? While this challenge is so big that we should probably all get together in an as good and as big as possible team to get as far as we can, rather than focusing on us being positioned better than our neighbors in this race towards building this computer.
Yes, and well, when it comes to the hybrid methods, of course, this is also something that has to be taken into account when considering, for example, the energy, going back to the energy calculations, whether it will be something that will allow us to have more energy-friendly computers, because very often we will be working with and in cooperation with high-performance computers. But definitely, the next paradigm, I think in the short term is precisely a combination of the two in exploiting the best from both of them.
Thank you.
We are running out of time, but I think we've got time for one more question from our in-person audience. So please keep your questions and your answers short.
Okay, thank you. So from an industrial point of view, normally nowadays we are tackling deterministic problems, right? Especially in the optimization problem and so on. And quantum mechanics and therefore quantum computing is a more or less probabilistic theory. So, and we need to really get the probabilistic right, we need to kind of sampling in an infinite amount of time, right? So really to come to this point. So therefore, do you really think we are tackling, or we are thinking to tackle the right questions by trying to search or trying to solve the deterministic problems with quantum mechanics, or do we need to find kind of more stochastic problems, like using uncertainties and so on in our problems, which are really then solvable with quantum computing, or is the other thing kind of deterministic problems to solve with quantum computing something, illusionary?
Thank you.
Sounds like a question for Max Planck.
Yes, indeed. But take into account that the quantum algorithm that exists, like Shor's algorithm, I mean, of course, you have this superposition of all the possibilities, but the quantum algorithm is very clear. And at the end, this superposition disappears. And it's deterministic, basically, what happens at the end. So it's only in between that is, let's say, in this superposition. And at the very end, then you make sure, or you can make sure that this is deterministic. But on the other hand, yes, in going to what you say, this is why people have hopes in things related to machine learning, so to accelerating machine learning, because these are, at the end, you want to kind of have a probability distribution with which you like to sample, and there is where quantum computers seem to be very natural, even though, I mean, at the moment, it's not very clear the Boolean acceleration in that case.
Thank you. One last question to Horst Weiss. If you want to acquire more money for quantum computing development at BASF, what would you tell people who have to give the money?
So first of all, I'm not going to acquire more money, because we started our endeavor after a lengthy internal process where we first made a strategy, and we're thinking about what would be possible beneficiary use cases and stuff like this, right? And for this, then you make a breakdown for a suitable structure, and the structure is planned in a way that it can have a critical mass for tackling certain problems, but at the same time is not over-exaggerating, and finally would run to justification of the overarching headcount every time. I mean, that's I would say, a typical industry business. You must clearly know what you're doing. It's a long-term effort. It's not a case where you would promise something like a quick return on investment and so on. That must be well balanced, and this is, I think, what we did.
But I'm happy to hear that at BASF you have enough money for quantum computing development.
What do you want to say?
Thank you so much. I think I'll take some terms with me. One is we are still early in the game. Yeah. Next thing is we are really talking about possibilities. We're not talking about certain things here. We're talking about a lot of potential, but we talk about promises. And the balance is, or the challenge is to keep the balance between, on the one hand, things we can and we must maybe also promise or we can foresee on the one hand, on the other hand, to manage the expectations that they might not come back to us at some point and even maybe destroy the support that is out there. And I think this is a big challenge for quantum computing, for quantum physics in general. And I think today in this panel we really managed this expectation and this challenge very well. And so I'd like to say thank you to all of you. Thank you so much to all of you. And I think it's worth a big applause from the audience to our panelists. Thank you so much, and I wish you more inspiring conversations, more inspiring opportunities to learn here at Falling Walls. Thank you so much. Bye-bye.